Hey guys, let's start with heat. Metal block A of mass 400 grams. Let's just highlight the key factors here. And an initial temperature of 80 degrees Celsius is immersed in 200 grams of water with initial temperature of 25 degrees Celsius. Here we are given the specific heat capacity of A and also the specific heat capacity of water. What is the final temperature of water? So here, first we are assuming after thermal equilibrium has been reached. So let's just review what thermal equilibrium is. Two things happen at thermal equilibrium. There is no net flow of heat. Not that there is no flow of heat. Heat still flows between the two objects, but they flow at the same rate. Therefore, there is no net flow of heat. And the second thing is that objects will have equal temperature. Objects have the same temperature. This is when thermal equilibrium has been reached. So when thermal equilibrium has been reached, now we can measure the heat change in each object. So in this case, we started with the hotter object being A with 80 degrees Celsius, and then we have water with 25 degrees Celsius. So there is going to be a net flow of heat in the beginning from the metal block A into the water, from the hotter object into the colder object. So this is the net flow of heat, which means A is going to lose heat and water is going to gain heat. So let's start with that. By conservation of energy, heat energy lost by A mass equals to the heat energy gained by water. This is of course assuming an ideal scenario where no heat is lost to the surrounding. So heat lost by A must be gained by water. Now let's remember the formula for heat energy. Formula for heat energy is Q is equals to mc delta theta. So this can be heat lost or heat gained. It doesn't matter. Q is equals to mc delta theta. So let's apply the formula here. So when we are talking about heat lost by A, we use mass of A times specific heat capacity of A, small c is specific heat capacity, times the change in temperature of A, and this must be equals to the mass of water multiplied by the specific heat capacity of water multiplied by the change in temperature of water. The question is to find the final temperature of water. So let's call the final temperature theta. So now we can substitute the values. M, A and Ca is given to us in the question. So the mass of A is 400 grams. Now here we have to be careful because the specific heat capacity's unit is joules per kilogram, and therefore we cannot use our mass in grams. Mass must be in kilograms. 400 grams is just 0.4 kilograms, and water will be 0.2 kilograms. So we have 0.4 kilograms, 0.4 multiplied into the specific heat capacity of A is 1000 joules per kilogram per degree Celsius. So this is 1000, and the change in temperature. So here heat is lost by A, which means theta is actually a lower temperature than the original temperature since heat is lost. So we need to put 80 first because 80 is larger than theta. So we have 80 minus theta. So this is the heat loss by A. Now we equate it to the heat gained by water. So the mass of water here is 0.2 kilograms. Specific heat capacity of water is given as 4200. And the change in temperature. Now for water, heat is gained by water. So the temperature is going to increase. Therefore we put theta first. Theta minus the original temperature of water. Initial temperature of water was 25. Alright. Now all we have to do is simplify and solve for theta. As we work this out, we will get 32,000 minus 400 theta. This is equals to 840 theta minus 21,000. So you can go on and complete all the steps. The final answer we will get is theta is equals to 42.7 degrees Celsius. Let's look at transistors. So this is a diagram with a transistor in it. Before we attempt the question, let's look at the diagram. This diagram is not complete yet. So first let's label the terminals of the battery, the dry cell. This is a positive terminal and this is the negative terminal. Alright. So for this to be functional, a functional circuit, you have to see the flow of current from the dry cell. So the flow of current from the dry cell, it's coming out from the positive terminal and going into the negative terminal, which means the current will be going in here. The arrow in the transistor actually follows the direction of current. So there we have it. Now it's complete. This would be an NPN transistor because the arrow is facing down, arrow is coming out, so NPN. So here we have to label the legs. We have the collector, we have the base, and we have the emitter. Now we have two separate circuits here that we want to focus on. In the transistor we have the base circuit, which is here. This is the base circuit. And then we have the collector circuit. The collector circuit is here. Collector circuit. So the base circuit controls the collector circuit. If the base circuit comes on, collector circuit comes on. If the current in the base circuit, which is known as the base current, is too low, then the transistor cannot switch on because the collector current will be low. So let's look at this. First, let's label this. This is base current, IB, and this is the collector current, IC. Let's look at the question. The transistor is switched on when V2 is greater than or equals to 1.5 volts. So let's just note that V2 is here. Calculate the minimum value of R2. So we're talking about the resistance of the resistor when the transistor is switched on. So the criteria for the transistor to be switched on here is that V2 must be at least 1.5 volts. So let's work based on the lowest value, 1.5 volts. For the potential divider, this is the potential divider. When two resistors are connected in series, then we have ourselves a potential divider. A potential divider does exactly what the name suggests. It divides the potential. So the EMF from the dry cell is split between the two resistors. They must share it. And the sum of potential difference must be equals to the EMF supplied. It cannot be more, it cannot be less. So let's work on that. The formula we use to find the potential difference across one of the resistors in a potential divider is this. The potential difference V, let's call it V2, since we are focusing on V2. V2 will be equals to the value of the resistance of the resistor, R2, resistance of whatever component is there, over the sum of resistance of both components in the potential divider, so R1 plus R2, multiplied by the EMF, V, the voltage of the battery. So in our case, the condition for the transistor to be switched on is that the voltage V2 must be 1.5 volts. So let's put that in, 1.5 volts equals to, so we want the value of the resistance over R1's value is 1.2 kilo ohms. So 1200 plus R2 times V. So V here is the EMF by the dry cell, 6 volts times 6. Now we just have to work this out. We will get 1200 plus R2 is equals to 4R2. So when you work this out, you will get R2 is equals to 400 ohms. So this is the minimum value of R2 for the transistor to be switched on. Let's look at how the transistor functions as a switch. One of the components in the potential divider here is a thermistor. In this syllabus, of course, we only use NTC thermistor. This is a thermistor. Now again, let's just complete the diagram. So this is positive and negative, and therefore for this to be functional, the arrow needs to go down. This is an NPN transistor. So let's look at this. When the thermistor is up, so let's say it is hot. Now it's hot, so there's a lot of heat. Heat is being supplied to the thermistor. When the thermistor absorbs heat, what is going to happen is the resistance of the thermistor is going to drop. So the thermistor is a non-ohmic conductor where the resistance drops when exposed to heat. So when the resistance drastically drops, what is going to happen is the potential difference across the thermistor is going to drop. Now this is based on the formula that we used earlier. Let's just write that down again. So the potential difference across the component will be equals to the ratio of the resistance of the component over the sum, the total sum of resistance. So resistance of component plus the other resistance multiplied by the EMF supplied multiplied by V. So as you can see, if the value of the resistance of the component goes up, the potential difference across the component is also going to increase. Now, when it decreases, it also decreases. So it works both ways. When the potential difference across the thermistor decreases, then the potential difference across R2 is going to relatively increase. Because remember, the sum of potential difference here of each component in the potential divider mass equals to our EMF. Mass equals to 6 volts. So when V1 drops, by comparison, V1 is going to be higher. V1 is going to increase. So when the potential difference here increases, remember this is our base circuit. When the potential difference across R2 increases, base current is going to increase, IB. The value of the base current is going to increase significantly, and what this is going to do is, this is also going to increase the collector current, IC. So remember, we have collector, base and emitter, and what will happen is there will be a significant enough collector circuit for the transistor to be turned on. So this is how it works. When there is heat, first the resistance of the thermistor decreases significantly, and the potential difference across the thermistor will follow. So it will decrease as well. While the potential difference across the thermistor is decreasing, the potential difference across R2 will increase relatively, because their sum has to equals to the EMF. So when the potential difference across R2 increases, the base circuit, the base current will also increase. This will cause the collector current to increase as well, and therefore the transistor is switched on. So when the collector current increases, what happens is the light bulb will come on. So in our setup here, the light bulb will come on when it is hot. So this can also be connected to an alarm system. So for example, if we are using to detect fires, let's see what happens when we put the thermistor at the bottom. So instead of here, let's put the thermistor at the bottom. In this scenario, when it is hot, so when it is cold, the resistance of the thermistor will be high. When it is hot, when there is heat, what happens is the resistance of the thermistor is going to drop, and therefore the potential difference across the thermistor is going to drop as well. Relatively, the potential difference across R2 is going to increase. Now here it doesn't matter because we are concerned with potential difference in the base circuit. Now, when the potential difference in the base circuit drops, so what's going to happen is base current is going to be very small. When base current is too small, then the collector current will be very small as well. So what happens is the transistor will not be switched on. So there won't be any light. The bulb will not turn on because there will be not enough current in the collector circuit. When it is cold, the resistance of the thermistor is going to increase, and therefore the potential difference across the thermistor will also increase. Now in this case, the base circuit will have a large current, so the base current will be high, and therefore the collector current will also be high, and the bulb will turn on because there is enough current flowing through the bulb for the bulb to turn on. So the transistor is switched on. So this case, when it is cold, the light bulb will come on, whereas when it's hot, the light bulb will turn off. So when we use the thermistor as one of the components in the potential divider, it essentially acts as an automatic switch that detects heat. Now what about light? So the same concept applies here, except in this case, instead of a thermistor, we use an LDR. So this here is an LDR. LDR stands for light dependent resistor. Now a light dependent resistor is made up of semiconductor. So when it is exposed to light, what happens is the semiconductor has greater number of free electrons, and so the resistance drops because the current flows. The amount of free charge available increases. So when there is light, the resistance of the LDR drops, R decreases. When R decreases, potential difference drops as well. So what we are going to have is low base current. Base current is very low, and therefore the collector current is low as well. When the collector current is low, the transistor is not switched on, and therefore the bulb is not switched on. So basically when it's bright, the bulb doesn't come on. But when it is dark, there are not much free moving electrons in the light dependent resistor. Therefore the resistance is high. When the resistance is high, the potential difference across the LDR is high as well. This will create a large base current. When the base current is large, the collector current will be large as well, and the bulb will turn on. So when the LDR is placed in the base circuit, what we have is an automatic switch for the bulb to come on when it is dark. Now what happens when we swap places again? So let's swap places between R2 and the LDR. Now what happens when it's bright? When it is bright, when the light hits the LDR, what is going to happen is resistance is going to drop. There's going to be more free moving electrons, and therefore increase current and decrease resistance. So what will happen? The potential difference across it will drop as well. Relatively, the potential difference across R2 will increase. So now again we are concerned with the potential difference in the base circuit. So now the base current is going to be high because of high potential difference. So what's going to happen is the collector current is going to be high and the bulb will come on. So when we place the LDR up, when it's bright, the light will come on. So of course again we could connect an alarm in the collector circuit, and the alarm will go off when there is light. So now let's say it is dark, there is no light. When there is no light, the resistance of the LDR is high. Therefore the potential difference across the LDR is high. Relatively, the potential difference across R2 will decrease. When the potential difference is low, what's going to happen is the base current is going to be low, and therefore the collector current is going to be low as well, and the bulb will not light up. So in this case, we have a switch where the light comes on only when it's bright. Let's move on to pressure in liquids. So this is a manometer. The density of water is 1000 kilograms per meter cube. Calculate the density of liquid K. So here we're going to use the concept of pressure in liquids. So what we have here is a manometer. We have liquid K, and then we have water on one side, and then we have a level where there is a phase boundary between water and liquid K. So let's look at this. Now when we are dealing with pressure with liquids, as long as they are at the same level, they have the same pressure, and that's the concept that we're using here. This means the total pressure at M must equals to the pressure at N, because they are the same level. The fluids are at the same level. So let's look at M first. What is the total pressure at M? At M, we have, don't forget, atmospheric pressure. So the total pressure acting at M at this point here would be atmospheric pressure plus the pressure exerted by liquid, which in this case is water, by 12 centimeter of water. So we have the pressure of liquids. Let's just go through the formula for pressure of liquids. P is equals to H rho G. H is the height, rho is the density of the liquid, and G is gravitational acceleration. So let's write that, plus pressure of water. Now this must be equals to the pressure at N. So at the pressure at N, once again we have atmospheric pressure plus the pressure exerted by liquid K. Now all that we need to do is substitute the values. The first thing you will notice is that we can subtract atmospheric pressure from both sides of the equation. So we have eliminated atmospheric pressure. We are left with pressure of water equals to pressure of liquid K. Let's fill in the values. So H rho G, height of water times the density of water times G must equals to height of liquid K times density of liquid K times G. So once again, we can eliminate G from the equation, divide the whole equation by G. So we get height of water times density of water equals to height of K times density of K. Now let's just put in the values. Generally, we want to ensure that the equation, the units in the equation is homogeneous. So the unit of density here is kilogram per meter cube. So let's just change it to meters. 12 centimeters will be 0.12 meters and 10 centimeters will be 0.10 meters. And now that we have it in meters, it's time to substitute. So the height of water is 0.12. 0.12 multiplied by the density of water is given as 1000 kilograms per meter cube, and this is equals to the height of K is of course 0.10 meters. So we have 0.10 multiplied by the density of K. So now we can just rearrange and make density the subject of the equation. Now we will get 0.12 times 1000 divided by 0.10. So what we get here is 1200 kilograms per meter cube. This is the density of liquid K. Let's move on to transformer calculations. Now let's look at question number 4. So let's just study the diagram first. What we have on the left is a power supply, AC power supply of 240 volts. And then we have the transformer, and then we have a bulb on the right side, and we have a diode. So what is the type of transformer? So how to determine the type of transformer? There are only two types, either a step up or a step down transformer. So when we look at this, you can see the number of turns of coils. So we have more on the left and less on the right. So it's going from more to less, which means this is a step down. This is a step down transformer. If the number of turns on the primary coil is 720, calculate the number of turns on the secondary coil. For B, we are going to be using the directly proportional relationship between the number of coils and the potential difference. They are directly proportional. So the higher the number of coils, the higher the potential difference. So let's use that. So here we want to find the number of turns of secondary coil. So I'm going to start with that. NS. So just for reference, the primary coil is from the power source. So this is the primary coil. We are going to label it as P. The secondary coil is here. So here, the ratio of the number of turns in the secondary coil to the number of turns in the primary coil is equals to the ratio of the potential difference, the secondary circuit, over the potential difference in the primary circuit. So this is what we get. Now to use this formula is very simple. So we are looking for the secondary number of turns in the secondary coil. This is why I started with NS as the numerator. So NS over NP, the number of turns in the primary coil is 720 as given to us in the question. So this is 720, and this is equals to, now let's look at this. The potential difference across the primary coil is 240 volts. And now we have to assume that the bulb is lighting up at normal brightness, and so we would assume that the potential difference across here is 6 volts. And we're going to ignore any potential difference that might occur across the diode. So we take 6 volts. So what we have is 6 over 240. And all we have to do is solve for the number of secondary coils. This will be equal to 6 over 240 multiplied by 720. So this will give us 18. So the 18 turns on the secondary coil. Assuming this is an ideal transformer. What does an ideal transformer mean? An ideal transformer, there is no loss of energy. So the energy transfer is 100%. The efficiency of the transformer is 100%. No energy is lost. So calculate the current in the primary coil if the bulb lights up with normal brightness. So the bulb lights up with normal brightness. We want to know the current in the primary coil. Now in this case, we are going to use conservation of energy. So the rate of energy consumption on the left and the right is the same since there's no energy loss. So we say power on the left and power on the right is the same. We need to use P is equals to IV here. Power is the product of current and voltage. In the circuit with the secondary coil, we have 12 watts of power. We're going to ignore any potential difference that might occur across the diode. We're going to assume that it's negligible. So let's just take 12 watts of power here. So we have 12 watts. P is equals to IV, so IPVP is equals to 12. And we already know that VP is 240. So 240 times IP must equals to 12. And so we can solve this. IP is equals to 12 over 240. This is equals to 0.05 ampere. This is the current flowing through the primary coil. Next, let's look at refractive index as well as total internal reflection. Let's look at this prism here. We can see light going into the prism. The angle given here is 50 degrees and 22 degrees. Now calculate the refractive index of the prism. So when we are calculating the refractive index, here we have to use the formula refractive index N. Refractive index N is equals to sine of incident angle over sine of refracted angle, sine I over sine R. When we are taking I and R, we must always be aware that this is the angle between the light ray and the normal, not the surface. So here we have the normal, the angle between the normal and the light ray is this. So we cannot take 50 as our incident angle. So this is 40 degrees because this is 90 degrees. It is the normal. And therefore, this is I and 22 is R. 22 is the angle between the ray as well as the normal. So this is the refracted angle. So this will be equals to sine of 40 degrees over sine of 22 degrees. And this will give us a value of 1.72. Now that we found the refractive index, we can attempt the next question. Calculate the critical angle of the prism. Let's just review what a critical angle is. Let's say we have a boundary here between, let's say, glass and air. So the light has to travel from a denser object, optical density of course, from a denser object to a less dense object. So here, remember we are referring to optical density, and then we have the normal. Right. So what is the critical angle? The critical angle is basically the incident angle. So as the incident angle increases, what will happen eventually is the refracted angle will be 90 degrees. So this is R. Now when the refracted angle is 90 degrees, the incident angle now is known as the critical angle. So the critical angle is the incident angle when the refracted angle is 90 degrees. Now this can only occur if light travels from an object with a higher optical density to an object with a lower optical density. So we are looking at glass to air in this situation. But the formula for critical angle is, here we can use the relationship with refractive index. So n is equals to 1 over sine of critical angle, 1 over sine c. Now we can just substitute value of 1.72 inside refractive index over sine c, and then we can do sine c is equals to 1 over 1.72, and therefore c will be equals to arc sine or inverse sine of 1 over 1.72. and this will give us a value of 35.5 degrees. So the critical angle for the glass prism is 35.5 degrees. Now we can answer C. What will happen when light strikes side AC? So we are talking about the ray of light. What happens after it strikes AC? Now we have to first find out our angles. Without the angles, we cannot do anything. So let's look at this. First we have our normal. Let's draw our normal. This is the normal. Alright. So let's look at the angles here. What do we have? We have 60 degrees and we have this angle here. So this is just 90 minus 22, which is equals to 68 degrees. And since we have the triangle here, this is 180 minus this angle 60 minus this angle 68. What we get here is 52 degrees. The incident angle here, this is our incident angle. This incident angle will be 90 minus 52, which is 48 degrees. So here the incident angle is greater than 35.5. The incident angle is greater than the critical angle. So what will happen when the incident angle is greater than the critical angle? So when we go up even further, what will happen is we get total internal reflection. When the incident angle goes above the critical angle, what we get is total internal reflection. If you've enjoyed this video, please help me by hitting that like button if you've learned something. If you'd like to see more videos like this, please do subscribe. All the best for your exams. I'll see you in the next video.